Pluto is a far-off and furtive, more unassuming planet that was once a piece of our close-by planetary gathering. However, recent, unsettling declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They propose that this cold world is on a potential impact course with Neptune. But how could this actually happen, and what might be the consequences of such a huge event? Are we witnessing a bizarre cosmic anomaly, or is there something more to this impending catastrophe? Join us as we explore the possible consequences of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent theories by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential, perilous crash between these two celestial bodies, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is highly eccentric, deviating widely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its 17-degree tilt relative to the ecliptic plane. Compared to other planets, Pluto's orbital inclination adds a layer of complexity to its trajectory. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, challenging our expectations of planetary positions. This raises a natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers attempted to map its unique path. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentricity. The mystery deepened when scientists realized that Pluto's orbit does, in fact, cross Neptune's. Despite this, Pluto's stability is a testament to the intricate mechanics of celestial motion. The three-body problem in space involves predicting how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravitational forces. This problem makes predicting their future positions incredibly complex. For Pluto, this phenomenon is explained through terms like asynchronous libration, orbital precession, and the VZK oscillation. According to astrophysicists, what keeps Pluto and Neptune from colliding is asynchronous libration. This term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from intersecting. Orbital precession, on the other hand, refers to the gradual shift in Pluto's orbit over time. When Pluto is closest to Neptune or any other giant planet, it is positioned well above their orbital plane, adding another layer of protection against collisions. Another critical factor is the VZK oscillation, named after three scientists, Vashkov, Zelnikov, and Kai, who studied gravitational interactions in space. This oscillation describes how Pluto, Neptune, and the Sun interact gravitationally, influencing their movements over time. While Pluto's orbit appears chaotic, the VZK oscillation ensures that it remains stable over long periods. These forces work together to prevent Pluto from crashing into Neptune or veering off course. The three-body problem is essential in understanding how celestial orbits evolve due to gravitational interactions. Studying these mechanics helps astronomers gain insights not only into Pluto but also into our solar system and distant planetary systems. Mathematical simulations in the late 1980s revealed that, despite these stabilizing forces, Pluto's orbit is actually unpredictable in the long term. Even small deviations in initial conditions can lead to significant changes over millennia. However, these irregularities are counterbalanced by long-term orbital stability, preventing catastrophic disruptions. Ongoing research has shown how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This orbital resonance helps maintain Pluto's stability. However, Neptune is not acting alone. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, with Saturn contributing as well. These gravitational interactions suggest that Jupiter, Saturn, and Neptune work together to ensure Pluto remains on a steady path for potentially millions of years. Without these stabilizing forces, the solar system would be a much more chaotic place. If left unchecked, objects like Pluto could collide with other celestial bodies or be ejected from their orbits, triggering a chain reaction of cosmic disturbances. For Pluto, especially amid discussions about its potential collision with Neptune, understanding its orbital mechanics is essential. This provides a clearer picture of the dynamic nature of our solar system. Pluto's case demonstrates that even the most seemingly unstable orbits can achieve equilibrium through the complex interplay of gravitational forces. It also highlights the importance of continued observation and study of planetary motion to deepen our understanding of the universe. The study of celestial bodies often confronts us with unexpected phenomena, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, where small changes in a celestial body's position or speed can drastically alter its future trajectory, is vividly illustrated by Pluto. Automated simulations have played a key role in helping researchers understand its movement. These simulations use advanced mathematics to model gravitational interactions between Pluto, Neptune, and other celestial objects. By adjusting tiny parameters in these simulations, scientists can observe how even minor changes can lead to dramatic shifts in Pluto's orbit. The future of Pluto's orbit, stability or chaos. Despite the intricate gravitational interactions that maintain Pluto's stability today, scientists acknowledge that the solar system is not a static place. Over millions of years, the orbits of celestial bodies can shift due to tiny gravitational influences, often referred to as chaotic perturbations. Even though Pluto and Neptune currently avoid collisions due to their orbital resonance, the question remains, will this always be the case? Long-term simulations suggest that Pluto's orbit will remain stable for at least the next few million years. However, beyond this time frame, small perturbations, such as the influence of passing stars, interstellar objects, or even tiny shifts in the Sun's gravitational pull, could gradually alter its trajectory. One possibility is that Pluto might be ejected from the Kuiper belt altogether, becoming a rogue planet drifting through interstellar space. Alternatively, its orbit could shift into a more elliptical path, increasing the likelihood of gravitational interactions with Neptune, Uranus, or even Jupiter. Could Pluto ever pose a threat to Earth? While a direct collision between Pluto and Neptune is highly improbable due to the stability of their resonance, some theorists have explored hypothetical scenarios in which an external force disrupts Pluto's current path. If Pluto were to be perturbed significantly, it could alter the dynamics of the outer solar system in unpredictable ways. For example, if a large, undiscovered planet beyond Neptune, sometimes called Planet 9, existed and had a strong enough gravitational pull, it could theoretically nudge Pluto onto a collision course with another celestial body. Though speculative, this highlights how the gravitational balance of the solar system is delicate and subject to change over astronomical timescales. That said, even in extreme scenarios, Pluto would be more likely to be flung into deep space than to veer toward the inner solar system. Given its current position and trajectory, the likelihood of Pluto ever posing a threat to Earth is virtually non-existent. The role of advanced simulations in predicting celestial events. To better understand Pluto's long-term motion, scientists rely on advanced computational models that simulate gravitational interactions over billions of years. These simulations use data from NASA's missions, including the New Horizons spacecraft, which provided the most detailed images of Pluto to date. Using these models, astronomers can make highly accurate predictions about planetary motions, potential collisions, and orbital shifts. While no immediate danger exists, these studies offer insights into how solar systems evolve and how minor changes in planetary positions can have significant consequences. The bigger picture, Pluto as a cosmic time capsule. Beyond its orbital peculiarities, Pluto holds scientific value as a remnant of the early solar system. Composed of rock and ice, this distant world is believed to preserve clues about planetary formation and the conditions that existed billions of years ago. Recent discoveries suggest that Pluto may have an underground ocean, raising the possibility that even this frozen world could harbor some form of life. Understanding Pluto isn't just about predicting its motion, it's about unraveling the history of our solar system. Conclusion: Pluto's fate in the grand scheme of the cosmos. While Pluto's orbit is complex and subject to long-term variations, current evidence suggests that it will continue to coexist peacefully with Neptune for millions of years to come. The interplay of gravitational forces, orbital resonance, and planetary dynamics ensures that, for now, Pluto remains on a stable trajectory. However, as we continue to explore the outer solar system, new discoveries could reshape our understanding of celestial mechanics. Whether Pluto remains in its current orbit indefinitely or undergoes significant changes, one thing is certain: the study of planetary motion will continue to be a fascinating and ever-evolving field of exploration. Erratic and unusual. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet, despite this chaos, Pluto's orbit remains stable over significant time frames, like billions of years. This actually means that Pluto's journey around the Sun has a sort of order to it, even though it seems tumultuous at first. Predicting celestial movements, especially when they involve irregular orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide great tools for understanding and predicting the future movements of celestial bodies, they also highlight the limits of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Besides, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we've made enormous strides in understanding space, Pluto's case reminds us of how much our knowledge of the universe still remains limited. Grasping the gravitational impacts of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can profoundly influence the stability and course of other bodies within the system. So why are leading astrophysicists lately raising concerns about a possible crash between Pluto and Neptune, despite all these complex forces trying to keep such an event from occurring? Neil deGrasse Tyson, a prominent astrophysicist and a significant figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked domains of space. His position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment but as a significant adjustment in line with our growing understanding of the numerous bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions is what keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential crash with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that we may still have some secrets to uncover. Will Pluto collide with Neptune, or is this just another moment of confusion in the constantly changing universe? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the goal of revealing more of the secrets that lie beyond. The possibility of a Pluto-Neptune impact raises yet another question about the mysterious and fascinating universe in which we exist. The potential for a collision between Pluto and Neptune raises intriguing issues about the dynamics of the solar system, as it challenges our conventional understanding of planetary stability. The idea that two celestial bodies with such vastly different characteristics could collide is both unsettling and captivating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and that Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of components and mixtures believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is made mostly of hydrogen, helium, and other lighter components, with a deep, dense atmosphere. A collision between such disparate bodies would significantly affect their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only variable at play. The presence of Jupiter, the largest planet in the solar system, is another crucial factor. Jupiter's enormous mass, strong gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from wandering too far into Neptune's territory. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. However, despite the apparent risks, continuous research has also shown that the relationship between Pluto and Neptune is not as simple as a direct impact course. The gravitational resonance between the two planets, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a sort of cosmic lock that keeps them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. The protective mechanism of orbital resonance is not unique to Pluto and Neptune. Similar gravitational interactions exist elsewhere in the solar system, demonstrating how celestial bodies can maintain stability despite chaotic influences. For instance, Jupiter's moons, such as Io, Europa, and Ganymede, also exhibit a resonance pattern that helps keep their orbits stable over long periods. This kind of synchronization, governed by gravitational forces, is one of the many intricate balancing acts in our cosmic neighborhood. Yet, even with this stability, Pluto's orbit remains highly eccentric and inclined compared to the nearly circular orbits of most planets. This unusual trajectory raises further questions about its past. Some scientists theorize that Pluto may have been influenced by interactions with other trans-Neptunian objects or even a passing star in the early history of the solar system. Such encounters could have perturbed its orbit, locking it into the current gravitational dance with Neptune. Beyond just Pluto and Neptune, the Kuiper Belt, a vast region of icy bodies beyond Neptune, adds another layer of complexity to the solar system's structure. Objects in this region, sometimes called Plutinos, share similar resonant orbits with Pluto. This suggests that the forces governing Pluto's movement are not isolated but part of a much larger dynamic system. Looking further ahead, continued advancements in observational technology will likely shed more light on these orbital mysteries. Upcoming space missions, more powerful telescopes, and deeper computational models will help refine our understanding of planetary motion and gravitational influences. If new variables, such as yet undiscovered celestial bodies, come into play, our current understanding of the solar system's stability might need further revision. As for the lingering question of whether Pluto and Neptune could ever collide, the overwhelming scientific consensus is that it remains highly unlikely. The resonance mechanism, along with gravitational influences from other planets, acts as a safeguard against such a catastrophic event. However, space is full of surprises, and our knowledge is constantly evolving. For now, Pluto continues its solitary journey through the outer solar system, locked in an intricate gravitational dance with Neptune and the other celestial bodies that shape its path. The mysteries of its orbit remind us that, while we have come far in understanding the cosmos, there is still much more to explore.